This year I presented on the topic of advanced maintenance for digital substations. We talked about condition-based maintenance, we talked about network monitoring, and we also talked about the importance of documentation and version management. In my presentation, I also highlighted some real-life examples of how maintenance procedures have been applied in a pilot digital substation project Fitness. A lot of people have the concern about maintenance because often it's seen as one of the challenges in digital substations. The reality is maintenance is much easier in digital substations, but it's a paradigm shift of how you do maintenance, and it's more software based, it's more about network analysis. This is something probably which is not widely accepted or widely thought about when we do the design of digital substations, and maintenance becomes an afterthought. And because of this, there is a fear that the maintenance engineers won't accept digital substations concept. So it was very topical to make everyone aware that this is not anymore operating in silos, but you have to think about maintenance when you do the design, and the maintenance engineers need to be a part of it. Now, I'm a bit off topic here because neither I'm a maintenance engineer, let alone being an advanced maintenance engineer, but we have been operating the Fitness digital substation on our network for about a year and a half now. And we have some real-life examples where we have done maintenance in Fitness, so I'll be talking about those. But also, we have started an engineering process design to look at how we build our future digital substations. So I'll talk a bit in that context as well, why maintenance is important. Because I am not an expert in this field, my ways of looking at maintenance are quite simple, and I will summarize it in the last slides of the golden or the simple rules of advanced maintenance that I think are important. It'll be good to see if you guys agree with me. So we'll talk today about things to be aware of, things to do, things to report, and of course, it's the circle of life. It's not something that you think about as an afterthought. Maintenance definitely is not an afterthought. It's something that runs during the entire process of when you start specifying to when you replace a system. So, the general understanding, or something that I've heard many times people say, is that you start with maintenance once you have commissioned the system. And the quote at the bottom is actually from myself, where I think maintenance actually starts with the first draft of specifications. You cannot think about maintenance after you have finished commissioning the system. You have to start thinking about it the moment you start specifying. Of course, the regime of maintenance and how maintenance is done will become more complex as you move through the project, but it is not an afterthought, and I think this is where sometimes we go wrong, because we later on think about how we're going to maintain the system after we have done the complete design and commissioning. So, some of the things that we need to be aware of course, digital protection systems based on IEC 62150 have a different set of maintenance requirements as that to the conventional protection and control systems, which are hardwired. They have many similarities. I'm not going to read them, but I think we are all aware of it. But there are some differences, and the major difference for me is because it's all so connected over the communication network, and it's an entire system that we look at instead of discrete IEDs. It's a system-based maintenance that we need to be working on when it comes to digital substations. And also, it is very, very necessary that when and where required, we do enable continuous monitoring of the communication network. And I will show you some examples where they have helped us in Fitness in troubleshooting, and actually have helped us understand what goes on in the system. And of course, it has to be an increased focus on cybersecurity. I disagree that digital substations are only things that require cybersecurity. I think conventional protection systems also have cybersecurity requirements. Of course, it's a bit more, it requires a bit more focus when we go to digital substations. Okay, we'll start with maintenance, talking about specifications. So, it's much easier to maintain a system which has been designed keeping in mind how your actual protection and control system is going to look like in next 5 to 10 years. And I only say 5 to 10 years because I think, Alex was talking about, protection is going to change a lot in next decade. So we are not really designing a system for next 20 years or 15 years even. I would say we're designing a system for next 5 to 10 years. But even if we can think about what requirements we might have, Is this system going to be bigger? Are we going to add in another feeder here? Are we going to extend it by any way? Is the functionality going to change? And it's giving that thoughts when you specify a system, even if you don't require all the functionality and all the capabilities right at the beginning, makes maintenance easy, because you have then made provisions for the certain use cases that you think that might pop up in the future. It does add to the cost because you're probably slightly over-specifying the system, but it's not that bad a deal, because sometimes those specifications don't cost you anything, but they save you a lot of hassle when it comes to future and future extensions of the system. So think of maintenance when you think of specification, and that's where the journey starts. Then one of the things I also want to talk about, something we have recently tried in our digital substations initiative, is flexible product naming and how that aids maintenance. One of the shyness of lots of engineers who work with 6150 systems comes from the fact that they do not understand the different device models, or they struggle with the different device models that the manufacturers have. And the main challenge comes, and this has been in my own experience, you're looking for a switch position, for example, and each of those switch positions, or the SESWI, whatever logical node it is in different places, in different devices. And I have the challenge when I'm working under a stressful condition and I'm trying to figure out what's going on, and I have to scroll through the device model of each of the IED, I've lost a lot of time. So if we can harmonize it by specifying and asking IED manufacturers to provide us with flexible product naming and flexible logical device structure, we can save ourselves a lot of hassle when it goes to maintenance, because our engineers need to only remember our specification and how we have designed it. There will be slight discrepancies, but they're not as big as when you have to really every time learn a system. And that is what saves you a lot of time when you're in a high pressurized situation and you're doing maintenance later on. So definitely recommend that. Definitely ask utilities to invest in specifications, invest in selection of IEDs that allow you to design it the way you like it to be. And that will make your engineers happier as well, because they didn't have to just familiarize themselves with one device model. Okay. The next thing after specifying, of course, is the engineering design. Do not hurry with it. Be careful, because the design itself can allow you to just define your GUs and your reports and you're done, and it will do the job. But when it comes to people being comfortable with the system, a good engineering design helps. So what you see here in an example on the left is a well-designed system where the IEDs have been grouped according to the base. It's got some switchgear symbols as well that actually give you the real switchgear information from the field. And we are using a tool to visualize this SCD file. This is a direct import from the SCD file. And on the right, you have this similar system, but a flat structure of IEDs, and you might have 40 IEDs in the substation. And they both work. They will both do the job when it comes to functionality. When it comes to your maintenance engineer going into the substation and actually looking at one of those visualizations and figuring out what's going on the system, I think they will prefer something which is a bit more structured. So it is an extra step. It does require definition of more elements during your engineering design, and probably the engineering design engineer can ask, why do I need to spend time doing it when I can do it quick and be on site? But it does, in longer term, pay off to think about the engineering design and how you structure your SCD file, because that really aids with the tools that you might use in future and how the tools visualize what's going on in your system. And think of it as a system, don't think of it as a device. A more whole system approach to thinking about digital substation designs really help you when you come later to maintenance, because we tend to, as engineers, get very, when we are designing a system, want to show off our knowledge about how we can use many IEC 6150 functionality to design a very complex and interesting system. But take a step back and put yourself in the shoes of someone who is not familiar with this design, who is not working with you at the moment, but whose job is to maintain the system. So keep it in a way, or think when you are doing the engineering design about those people and how they are going to work and operate the system later on. So think about how they can segregate the network if it's required for them to do so they can take one bay out when it's required to maintain that bay. Think about where are my points of subscription, so it's easy to isolate them if they want to do any kind of replacement work. Think about the network bottlenecks and what they cause and what kind of issues they cause, so that when the maintenance engineer knows that, they can actually focus on those areas, or you remove those bottlenecks when you are actually designing your system. Think about how you can ensure seamless time synchronization, and then most importantly, how much redundancy you want to build in so it's easier for your maintenance engineer to actually take out one system at a time if the requirement be. Of course, a question always comes down to cost versus redundancy, but these are not only engineering design questions, these are questions for maintenance. So it really needs some focus when you're thinking about the system. And I say, when in doubt, keep it simple. You don't know what you're doing, you don't know how it's going to look like, it might cost you a bit extra, but keep it simple. Keep it PRP, point to point, easier to segregate, and that's the kind of design architecture we are going with, because yes, we can make it more complex, but at this stage when we are really trying to transition into digital substations and convince everyone in our company that it's the right thing to do, why not keep it simple? I know there's a slightly higher CapEx investment, but does it not pay off when you actually can make the transition and make it work? And once people are confident, you can go into more complex designs. Okay, and this is probably something everybody understands very well, and I don't need to stress enough. I will just talk about one element here. Whatever you do not drop the... Sorry, I didn't know how to pronounce that word yesterday, and my colleague told me about it, so it still remains a thing that I have to practice. Do not drop the baton. Okay, whatever you do not drop the baton. Whatever you do ensure that there is a clear thread of knowledge sharing within the business. Because one of the crucial things that people forget about is people leave companies, things change, and often, even if I have done the work, 3 months later, I might have no clue about how I have done it because we forget. So unless you write down things, unless you document and invest in version management, there is a very good chance that you will actually forget what you have done. So this is something, it's a golden rule, and no matter how painful it is, you have to write down things that you're doing. And one of the things I've added there is documentation of errors and resolution methods. It doesn't need to be something really complicated. It can be a simple wiki page, or it can be a simple guidance note. But once you have resolved a thing, then do document it. Because to give you an example, this is a real-life example, our tools, third-party tools or independent tools that work with all vendor IEDs, they're not perfect. Neither are the vendor ID tools perfect. I think we're all aware of that. Sometimes we do deploy ways which are kind of a workaround to solve issues. Then we don't document it. And another engineer coming and going through the same frustration of solving the same error in one way or the other and asking the same people the same question is probably one of the biggest waste of time when it comes to maintenance, but also when it comes to design. So write it. I know it's painful and we don't really write. We like to really go fast and do things, but it's so important and it's going to save yourself so much time in future that it definitely is worth some effort into. Okay. Now we will go to the more obvious points of maintenance, and we'll start with smart testing procedures. So yesterday when we were having our roundtable discussion, one of the points that came up is engineers tend to want to test everything again, no matter what it is when in the maintenance regime. You change a setting, they want to test everything. You change a configuration that doesn't really affect anything else, but they want to test everything. Let them do it. If that's what builds the confidence, why force them to go with the subset or a selection of tests? I know it makes sense, but until they gain that confidence, I think it will be very, very hard to convince them. It's all, it all comes down to learning by doing. So what we did in fitness and what we have created is a set of automated test procedures that almost does everything for you. You just have to press the button and the entire procedure runs by itself. To show you, right at the top, this automated test procedures not only sets up the entire sample value stream, goose configuration, and everything. It also enables the simulation flag and the test mode in the device that is testing. Then it runs through its set of tests that it needs to do, and right at the bottom, it disables the flags again. So the engineer just needs to know how to work with this procedure, but beyond that, it's all automated. Yes, it's running all the tests again, but probably the amount of time you'll require to run the tests all individually and then remember every right step you have to take to put the system back to what it was before you started with the maintenance regime. This is automated, and it goes smoothly through, and it's probably a couple of hours more, but it's not as intensive or as long as a procedure if you have to do it all by yourself. Another smart testing procedure that I want to highlight that we have used many times in fitness is when something goes wrong in this network or something goes wrong with the system and you have no idea what's happening, what's the first thing you can do? The first thing you can do is compare your last documented system configuration to what's on the network. And there are tools in the market that allow you to do that. So what you do is you take your last SCD file that you have documented after commissioning, that was the one that was signed off, you compare that to what's happening on the network, and if anything is not right, you will see that. So that is your first clue what's going wrong. If you really, really have no other idea or there is no other indication of any kind of failure, or any obvious indication of any kind of failure. So just two examples, there are many more that you can deploy under smart testing procedures to make your maintenance regime easier. Learning by testing, know your system limitations. It's very, very important to know what is the limitation of your system, and believe me, there is one. No matter how big the bandwidth, no matter how many clever IEDs you put, no matter how redundant you make your system, there is a point your system will break. And it's very important when you do your initial commissioning and testing that you identify these limitations. How can you do it? So in fitness, what we did, we deployed a method called negative testing. So we would purposely overload the network with random sample value streams or alarms, and we flood the network, and we will flood it to a point when the IED stopped responding or the SCADA system didn't get updated. And then we know, okay, it's that point that the system fails. Not only that, we also saw different IED behaviors, like some IEDs will start complaining when there is on their port, they have more than 80 goose per second or something like that. So these are the limitations that are not something you will face every day, but it's very important that you do perform this test and document it. So if a maintenance engineer comes and sees some erratic behavior on the network, they can first refer to the limitations of your system and see if you've reached one. Because there will be always a situation that you haven't expected, and these situations do arise when you operate the system on a daily basis. So that's something which is very important and key to designing and testing a proper system, but also important for maintenance, is knowing the limitations of what your system can do. Then, right tools. Cannot stress enough. Couldn't have done fitness without having the right tools that provide us with the visualization that we really, really need to identify what's going on in the network. Not only that, it allows us to drill down to the individual logical node, the data set, and see what's really the quality of things. So some of these examples are real-life maintenance examples that came up during commissioning, or they came up after we commissioned the system. And it's very easy if you have a tool that tells you what the problem is, rather than you looking through a set of maybe Wireshark files and pickup files trying to figure out what really is going on. And especially it makes it easier for people who are not very familiar with 6150, or people who still have to maintain the system but not really trained to know the exact structure of 6150. It's a first start information about what's happening on the network. But not only that, sometimes some of these things don't cause problems because they don't come into play until there is a fault on the network, and it just can go unnoticed if you're not regularly checking it. So tools enable you to identify issues before they become failures. And as I said, a stitch in time saves 9. So you have to be careful that, and you have the power right now, it's not actually careful, you have the power right now with digitalization and with communication network and better visualization that you can really see what's going on. It wasn't possible when you had hardwired IEDs. some failure in a hardwired IED, unless the IED really monitors and tells you what's happening, you would never know until there's a fault. But with digital substations, you do have the possibility to really drill down and see what's happening. You have the possibility to what you can call as predictive maintenance or condition-based maintenance. And you can see what's happening way ahead in time and actually do something about it. And these are some of those examples. The last one, this one being very important. Sometimes you have questionable data, and really there is nothing being alarmed or nothing really coming up, but it might be related to a more underlying problem. So the one here was actually the issue that there was an Ethernet cable used in a high voltage substation that wasn't shielded, and the sample values had CRC errors in it. And it took us a long time to find out what the issue was. But having a questionable data on the system and to be able to see it without doing just right there and not really drilling down much gave us the indication there is something wrong and we need to fix it. Enable continuous monitoring. Some of the things that you can do, okay, you might not be able to continuously monitor every aspect of your communication network, but you can enable port supervision, and I definitely recommend that. Because a port supervision screen like the ones you see here, and we have 2 SCADA systems in fitness, and you can see they both deploy port supervision. Some of them are 6150 based, some of them are SNMP based, but also not only the port supervision, they take the individual IED data qualities and they show you if there is a time sync fail, if there is a failure in the quality of the signal, if the IED itself is not healthy, and all these parameters are available as data attributes in all the logical nodes about the health of the IED, so why not use it? It takes a bit of time to create a port supervision screen like that, but when your maintenance engineer walks in, he has a first-hand information from this screen if something has gone wrong. For example, if this merging unit loses time sync or it does have a bad quality, it will show here. So it's just right there. You don't need to even think about it much. You can see it on the screen, and then you start your investigation from there. Of course, you can also have continuous monitoring, costs you a bit more, but really if the system is critical, that cost is probably nothing in the long run. If it provides you an even more detailed picture of goose communication, any failure in reports or sample values, even between the IEDs, by using the right tools. An example of where continuous monitoring actually helped us find a critical issue that went, and that was, that had some erratic behavior on our network. So what happened is we installed some LPITs in fitness, and they let me do it, which was probably not a good idea. So our structural engineer had designed a structure where the LPIT was placed, and the fiber was supposed to come from the bottom of the LPIT. But of course, we hadn't drilled a hole to get the fiber out from the bottom. So when we were installing it on site, I was asked what to do. And because that would have involved us going back and drilling a hole and getting an approval from the structural engineer, I said, okay, just get the fiber out from the side. So that's what we did. But what we created in that process is in the armored fibers, which are quite tightly wound around the fiber, the armor cable, we bent it. So what was happening is a couple of times, and everything was fine, we commissioned the system, no problem, went away. Then a couple of times I would notice that the fault recorders of the relays are picking up a signal or a fault, which was not on the network. So we compared this with the conventional system because fitness runs in parallel with the conventional system. Okay, that behavior is not there on the conventional system. So what could go wrong? Of course, if the fault recorder is picking up and is picking up a measurement, you can see that the sample values or all the signal it's seeing is not right. So we enabled continuous monitoring on the network. So we used one of those devices that can do trigger-based recording, and we set a trigger for any deviation in the sample value threshold to be recorded for a period of 10 seconds. So after we did that, a couple of times we captured waveforms like that were clearly not right. So we were able to extract the records and send it to the vendor for further analysis. And of course, rightfully, the vendor could identify the issue, replicate in the lab, and we found out the problem was bending an armored cable causes a physical stress. And when this stress releases itself because of variation in weather conditions or temperature, it causes a deviation in the light signal. And that's what was causing this kind of behavior. Of course, we still don't have a proper installation because it's too late, but we changed the armored cables with flexible fibers in conduits so they don't have that kind of mechanical straits, and the behavior was resolved. So again, quite a different maintenance regime. A fault, the thing was actually a physical, physical anomaly in the installation, but you can use your tools that you have or you have invested in to actually record and analyze behaviors that only happen once every 2 months or once every 2 weeks, and nobody can stand there watching it all the time. Okay, so.
You have the time there.
Oh, yes, of course. Thanks, Alex. I was just looking at there, I didn't look there. Okay, I don't actually have that many more slides left, so I think we have enough time to finish. Outage-less maintenance. So in addition to simulation flag and test mode allow you to do something called outage-less maintenance, especially important in transmission network where you have highly constrained networks. Again, going back to the things Alex spoke about this morning, you have wind farm generations, you have solar panels, you have biomass, and they are intermittent, and they require a continuous availability of the network to be able to produce and successfully transfer the electricity where it is required, or transfer the energy where it is required. Now, if you go around and try to take an outage on such a network now, it's becoming really challenging, especially in SP energy networks, because we are in an urban area, quite a tight system, and we've got lots of wind generation. Every time we want to repair something and we want an outage, it's a challenge. So how can the outage-less maintenance help there? So when you do addition to feature-based maintenance regime, and generally transmission protection systems do have a main 1, main 2, and then in cases as well a backup. So you can pretty much take one of the systems out of service without touching anything and putting the right flags on them. So what it will do is you put a test set and you simulate whatever faults you need to test or anything that you need to test. You take the IED out of operation. You take the signals that go from the IED out to the switchyard. You even put them, so that you put that into test block mode as well. So anything the IED does is only being tested with this test set. It's not affecting the real operation of the rest of the system, and your system is still protected because you have a redundant system protecting it. And once you finish your test, as I showed in the automated test regime before, you take all the flags out, and if you need to replace the IED, you replace the IED. If not, then you put it back into operation. It's a really powerful feature. We commissioned our entire substation, our entire fitness system using this, and I cannot recommend it enough. Again, going back to the point that the IED manufacturers have all implemented it in slightly different way, and probably some harmonizing is required there to make it also simple for the maintenance engineers. But we are almost there in being able to enable outage-less maintenance on our network. Last but not the least, and I will not talk much about it because cybersecurity seems like the theme for tomorrow, and there you'll see lots of good presentations about it. So ensure cybersecurity. It's very important, no matter if it's conventional or a digital substation. Cyber attacks are very real. They happen, and often it's just malicious attempts to cause trouble rather than a big plan to take down your system. So do deploy techniques that are out there, role-based access control, intrusion detection systems. You will hear a lot about it tomorrow, so I will not bore you with it. But one of the maintenance things to be aware of is ensure cybersecurity, because once a cyber attack happens, the work you have to do after that, not only to document what happened and take measures, but also to bring your system back up, can often be just a nuisance more than anything else. So with that, we come to the last slide where I write down the 9. I couldn't make up a 10th one. I thought about it. So 9 is the number I had to end at. 9 simple rules for maintenance, the way I see it. And as I said, I'm not actually a maintenance engineer. It's the circle of life. Maintenance starts with specification and ends with replacement. It's not something that you can take as an afterthought. Digital substations do have different maintenance requirements. Not only that, they enable new maintenance procedures through allowing you to see much more than in a conventional substation. So do make use of it. Think whole system is not an IED, it's a system. When in doubt, keep it simple. Sometimes it's better to optimize, but also keep in mind that you should have the ease of maintenance. Do not drop the baton. Do think about knowledge dissemination, knowledge sharing. Recording of things is not just for others, it's for you as well. And of course, the rest of it, do the right testing, ensure continuous monitoring, and ensure cybersecurity. Okay, I'm slightly over the question time as well, so I will be allowed only one question, maybe two.